Hello to everybody. It is a pleasure to introduce the next speaker, Professor Anastasios Sextos. He's a professor of earthquake engineering at the University of Bristol. He is the head of the Earthquake and Geotechnical Engineering Research Group and the academic lead for the design and delivery and director of a soil foundation structure interaction facility at the University of Bristol. He holds a dual appointment at the National Technical University of Athens, and he is a member of the European project team for the evolution of structural Eurocodes, and a member for the seismic design in UK, a co-chair of the work group 11 for bridges, and the national delegate of Greece at the European Association of Earthquake Engineering. Today, he will give us a talk on structural analysis for bridges, accounting for spatial variability of ground motions. Please, Professor Sextos, the floor is yours.
Very much for your kind introduction. So I would like to delve a little bit more on the specific aspect of seismic action, which is quite unusual in most seismic codes. In fact, it's not even considered in most codes worldwide. And in that regard, I think that the Eurocode 8, even from its previous version, was quite novel. Because of the nature of the topic we are talking about, I will take the liberty just to share a couple of slides here and there, just to explain the context for those who are perhaps not as familiar. That's obviously a Eurocode presentation and not a research talk, so I'll be very careful with that. But essentially, some basic words that can facilitate our understanding. So for the code, spatial variability is essentially a situation. It's a situation where ground motion between support points is different for whatever reason. And in such a case, the code is suggesting that we should not do uniform excitation analysis. That is, time history, response history analysis with a single earthquake record for all supports. You may see that also in the literature as multiple support excitation or asynchronous excitation, but for the code, for the Eurocode, is spatially variable earthquake ground motion. So even intuitively, we can understand that ground motion shouldn't be the same. The trick is how to calculate it and introduce it in a code framework. And essentially, in order to do that, the previous version and the current version are splitting the problem in the background in several different scenarios and phenomena that are running. One is the obvious fact that it takes some time for the waves to travel across different bridge supports. The second is that as the waves are traveling through the soil media, they are reflected, refracted, superimposed in all sorts of ways, and therefore they are losing their stochastic dependence, which practically means that if you compare two ground motions, they won't look the same. That's the second important thing that the code is taking into consideration. And this, if it is plotted versus measurements that have taken place worldwide, effectively lead to something that is called coherency, the stochastic correlation, or how similar they look like, if you like, in terms of phase and in terms of amplitude. Important thing, because that's in the code, this coherency, this correlation drops with frequency, drops with distance. So the longer that span between two supports, the less correlated the ground motions are. The higher the frequency, the less correlated the ground motions are. And this is nicely reflected in the code. Obviously, there are also some other aspects, like local site conditions, 1D effects, 2D effects, 3D effects, topography effects, as Paolo Professor Franchin previously explained. This is also somehow implicitly accounted in the code, as you will see. An important disclaimer here, when the bridge is short, and the time delay is not so important because of the short length, then these side effects dominate the problem, which is also qualitatively is accounted in the code. And effectively, this can be even more pronounced in case that the soils are not just different or site response is so different due to liquefaction effects or other special effects. So the less, let's say, uniform the soil is, the less correlated or coherent the ground motion is, the more different the bridge response is. And this was just a short introduction so that whenever we see something in the code, we understand what is what and why it is there. Another very important thing is that during the last 20 years, people working on bridge engineering noticed that when ground motion is different, we can just take the example of a bridge in Austria in this case. Then the response of the bridge, because of the fact that ground motions are not uniform as we do in our computers, is quite different because there are some modes, not any mode, typically the first and second antisymmetric modes, that if you just plot the Fourier transforms or you plot the contributor contribution in any other way, you will see that they are excited. And this is just a video to visualize. I promise I'll switch directly back to the provisions. Essentially, if we excite this specific bridge with a single ground motion, uniform excitation, or with a bunch of different ground motions that are partially correlated, and we run the response, if you're looking at the bridge from the top, you will see that the response of the bridge in the transverse direction as we're looking from the top, for synchronous excitation, the bridge is responding pretty much in its first transverse mode, whereas due to the more accurate asynchronous motion, it takes the shape of the first and second and third antisymmetric modes because of the waves that travel. This is fundamentally different, and that's what the code is taking, and that has been measured in other bridges. That's my last scientific slide, I would say. If you plot the response of a bridge, measured response, in the frequency time space, all of a sudden, when ground motion is different between different supports, an additional frequency of excitation appears, and this relates, if you see the mode, to an antisymmetric mode. So it is happening like 80–90% of the cases, but whenever spatial variability phenomena are important, that's part of the picture. And that's essentially what the code has been trying to do from the previous version. I'm now going directly to the code provisions. What the 2005 code was prescribing to account for this problem. First, it was offering the possibility to do something, which was pioneer for the time, really. Then it was offering a quantification of this phenomenon in some sort, at least in terms of when you should account for that and when you could neglect it. And thirdly, it was offering a simplified static approach. I'm just showing you a couple of slides about what the previous code was doing in case that you are familiar with that, and also to understand how the evolution is now made to something similar, but we think more accurate. So the code was essentially providing a table, rightly so, I think, essentially saying that if your soil is quite stiff, let's say type A category, then you are more tolerant in terms of spatial variability because most probably the soil is uniform, the soil is stiff, and therefore side effects are limited, and therefore correlation of ground motions looks more like the synchronous case that we're accounting for. So the softer the soil, the smaller the threshold length beyond which you should account for it. So the code was providing these simple rules where you should think about spatial variability and where you can neglect. Then it was offering, and this was really quite novel, but a little bit interesting for the time, definitely novel for the time, it was requiring the engineer to do two static analyses on top of the standard response spectrum or whatever nonlinear or linear time history or response history analysis. One was to excite the bridge essentially in post-static displacements with a shape that you can see here, this linearly increasing shape of support deformations. And the other was kind of a deformation vector where the sign was changing from one support to the other. Whatever the static situations, you were getting some design quantities out of two static scenarios. You had a conventional one, this was the third one, and you were superimposing essentially the design quantities out of these three scenarios. Now, the good news was that obviously you were doing something. The challenge was that A, this was static, and B, whatever the situation, the influence of spatial variability was quite low. So that was obviously in the right direction, but was not necessarily capturing the dynamic nature of the problem that we have been discussing now, which I think is now more properly addressed. This is how the static deformation scenarios looked like, and effectively, this was the simplified solution that was offered. But the previous version was also wise enough to offer a rigorous method as well, not easy to apply, but quite accurate. This actually is still standing as a method. The first equation is from the work by Professor Diodatis. The second equation is from the work of Professor Terkuregan in UC Berkeley. So essentially, it was also offering two rigorous solutions for those who were able to follow them. The one was that in case of a response history analysis, this is the way to generate your samples. Effectively, there was a factor L relating to the loss of coherency that I was talking to you about. Omega was the frequency, theta was the delay, and phi was effectively a stochastic parameter to introduce some randomness in the generated sample. So this was quite established method. Then there was also the option to run a multiple response spectrum analysis. So a response spectrum analysis in principle, where you would have a different response spectrum for each support if the soil was different. And the way to superimpose for that was essentially using this, not the easiest probably equation in the world, but definitely was something that was in the code and you could follow. An important parameter here is that D is the spectral displacement coordinate, if you like, and this row here was practically the correlation between two adjacent support points for all possible pairs. That's the reason for the various summations here. So this was what the code was prescribing. Now, in the new Eurocode version, the new Eurocode provisions, the committee has essentially stepped on the existing provisions by injecting some more recent, let us say, research that has been established elsewhere. So one important thing we need to clarify is that if you're looking for special variability effects in the code, you have to both look at the seismic action provisions in Eurocode 8 Part 1.1, because in principle, non-uniform earthquake excitation could also be applied in other structures. So that's a more general issue and therefore went to that part of the code. And also more specific provisions naturally for the bridge, for bridges, which is introduced in Eurocode 8 Part 2. So we'll be having some different tags depending on where different tables are coming from, just for you to be able to find them more easily. So first of all, the code for bridges is describing explicitly when we should take into account this specific problem. There are three reasons or three rules. Any of the three, if it applies, it will force us effectively to do something, and this something is prescribed in another table, this famous table 5.3. So when should we account for special variability? A, when the soils are quite different, and this is quantified by having an average VSH that differs more than 200 meters per second. Now, why is this number? Because this was the average difference between different classes. How you would define VSH for the entire soil profile? That's something prescribed in Eurocode 8 Part 1. So if your soils are different or too different, then you should do something according to the table. Or if your bridge is quite long, how long? This is the table. If for soil A, it exceeds 400 meters, for soil B, exceeds 300 meters, and so on. Thirdly, if your bridge is perhaps not so long, but you do have quite long spans, because effectively what we are talking about is correlation between different pairs, and that's not just an issue of the total length. It is also an issue that relates to the distance between adjacent peers. Therefore, if any of these three applies, you should do something. We'll come back to that, what you should be doing in each situation. It is also building the current version in the Part 2. It is building on the previous provisions that I just showed, the method presented by Professor Derkuragian. So in case you would wish to represent special variability of ground motion by a set of different support-dependent response spectra, and you would need to find these strange correlation factors from one point to the other for all possible pairs, then you can use this exponential factor. No surprise, this is a factor that drops with distance, is a decay factor, because like we discussed, the correlation between different ground motions drops with distance. And this is pretty much how this can be calculated. The only parameters that get into the formula are effectively the span length, which is a known number, the total length of the bridge, the characteristic length for different soil profiles. How do we know that? We know that because we do know the soil profiles, the soil category at each support of a long bridge, and therefore, not only we can have this factor here that reduces the correlation factor with distance, but also has an additional factor, the AKL, that accelerates this decay of correlation when the soils are less uniform, because effectively it subtracts the characteristic lengths of different soil piles, which means that the more different they are, the higher this coefficient, and therefore the quicker the drop of coherence. But if they're identical, say in the case of uniform axis, this all ends up to 1. So this is a very simple solution that is offered by the code for those who would be interested to do, let's say, more rigorous multiple response spectrum analysis. This is just for your information. If you would like to plot that in a chart, you would see that between different points, the further they are apart, the quicker the loss of their coherency, and basically the quicker the reduction of this correlation factor. And obviously that makes a matrix, because all pairs are involving all different support points. The correlation of motions in the same point is unity. The correlation, partial correlation of ground motion drops like with this. So effectively, this is in the right direction, it seems. It is also offering a set of advice, quick advice, what you should be doing, we should be doing when designing structures for spatial variability, assuming that it is required depending on the situation. So the basic distinction that is made on, let's say, in a vertical sense, is whether the bridge is short or long, but this also involves the span. So there are essentially two extreme situations. Either the bridge is short and has short spans, or the bridge is long or has long spans. In the first case, if the soil is uniform, the code is simply saying you should do nothing. You just have some rest, like the person here, or just have a cup of coffee and you're done with spatial variability. But if your bridge is long, or you have a long span, I'm sorry, that's a long span, not a short span, then essentially you should do something. And it is offering a simplified higher mode excitation method. We'll talk about this. I'm going to describe how this simplified method works. For those who don't like it or don't want to implement that, there is a way to get away, let us say, by essentially not applying the simplified method, but actually mostly apply a penalty, if you like, to the design quantities, increase the design quantities by 20% and get away with it. Now, there is also the case where the soil is non-uniform, so it's not uniform, therefore the spatial variability effect is more pronounced. So in case that the bridge is short and the span is short and it's a simpler, let's say, situation, yet the soils are very different, the code is suggesting to do what's important. It's not the wave passage that is important in this situation, mostly is the local site conditions. So the designer can simply do a series of one-dimensional site response analysis from the bedrock to the, let's say, the foundation input motion at the base of the support, calculate in this case the different accelerations at each support point, which is relatively easy to do with a shake type analysis or cyclic 1T or cybershake. I mean, there's a number of methods one could do this analysis. But if the bridge is long or the span is long, then you should do a proper spatial variability analysis, either in the time domain or in the frequency domain with multiple support response spectra, using the correlation factor that the code is providing. Then there is also the case that the designer wouldn't like to do that. And therefore, the code is offering the possibility for the designer simply not to do 1D effects and 1D side response analysis, but just prefer to get the penalty, increase the design quantities, increase them in 20% for the short bridge and span scenario, or increase it by 30% for the long bridge or long span scenario. That gives some freedom, some flexibility to the designer, I think, because not all design offices have the ability to do, or the confidence, if you like, to play with these methods. But it's clearly that with this approach, The more complex the problem, the more complex the method. But always the designer can get away with a simple penalty rule. And then in case that the situation is so complex that there are topography effects, 2D effects, 3D effects, and the like, then in this case, either somebody would apply a 30% increase in the design quantities or do a proper analysis, including the entire valley and do a proper site response model. When we're talking about seismic design effects or design quantities, essentially we mean everything we can imagine, all the EBPs and design numbers, bending moments, shear forces, displacements, relative displacements, everything that we're using to design is effectively amplified by a percentage if we don't want to use a more rigorous method. Few final slides on the simplified method that it is offered for the case of uniform soils. I'm gonna just save this slide as a concept. The rest I'm gonna pass quite quickly to finish on time. But the important concept behind these suggestions, so if the soil is uniform, you could something different that is quite easy to implement, pretty much along the lines of the previous Eurocode version of superimposing static situations. But instead of focusing on the ground motions, which in fairness, they're quite uncertain, and there is no confidence that you can do them in a framework of design in an accurate way, unless you do it probabilistically, which is not a design method then, it's something else. The concept now is shifted. The focus is shifted from generating samples, which we want to essentially amplifying quantities that are associated with the higher modes that are typically excited by spatial variability. So the code is not trying to say that spatial variability effects will be important. It says that if they are important, these are the structural members that are affected by the first and second antisymmetric mode, and therefore you'd better just amplify the design quantities for these selective 1, 2, 3 peers or whatever is affected by antisymmetric modes, and that's enough. Why? Because your soil is uniform. I know I'm not getting into the mathematics at all. I'm just saying 10 seconds per slide, that if somebody would like to do the simplified method properly, I mean, outside of the code provisions, what you would need to have would definitely be a target coherency, or how the coherency drops with distance, to know your soils, to do your model analysis and calculate model participation factors, to calculate the influence matrix, what would happen if a static displacement of a unit displacement is imposed in one support, what would be the displacements in the remaining structure, calculate model participation factors, and essentially quantify in a mathematical way the non-dimensional spatial variability parameters from one point to the other. This also involves the calculation of the excited antisymmetric modes and the quantification of how much these have been excited. So that's the background behind this, and I'm not talking more about that. But what the code is actually doing, the code is simplifying all this, assuming that the approach is more accurate to focus on the structure than focusing on the ground motions, and is actually asking the designer to do 4 different things, 4 simple things: to run a model analysis, then effectively to run 2 static analysis using the model profiles of the forces of the first antisymmetric and the second antisymmetric mode, amplified by a factor that it is parametrically identified in the literature. So essentially it's a pushover with a vector of loads, a static analysis. You get some design quantities out of this for the first antisymmetric, the second antisymmetric, which is quite easy. Then you run whatever analysis you would run anyway through response vector more time history, and then you simply superimpose. And really, if you don't like that, you can always take the 20% penalty option and get away with it. So this was just to simplify. I took the liberty to present it in a little bit more detail, just in case this is needed. So with that, I think I have concluded the overview of the provisions of the code. I would like to particularly thank Professor Pierre Labbe for his contribution through the committee, and Paolo for the leadership, Professor Franchin in running the PD6, and all good colleagues that were part of this committee. I'm very happy to answer to questions if any.
Thank you very much, Professor Sextos, for your very interesting presentation. And thank you also for keeping the time. We have a couple of questions that came in by chat. The first one is a general question. Does the second generation code relates to the British Standard Code? It's from Bantu Medicana.
Not necessarily. The British standards, in some cases, they're identical to the Eurocode. In some cases, they are different. These provisions, I think, are bespoke for the Eurocode.
Then we have a second question from Agatoklis, Khalifa University, to Professor Sextos. Is the randomness introduced by the uniformly distributed phi random variable sufficient to capture the record-to-record variability we see in recorded spatially correlated ground motions?
That's an excellent question by my good friend, Professor Yaraglis. First, let me say that this randomness, let's say phi parameter, was part of the provisions of the previous code. And because what you're saying is actually right, if you just introduce the randomness once, you will have the stochastic component between a single run of multiple points. This has nothing, is not enough, let us say, to account for the record-to-record variability, meaning if we rerun the analysis for a different set of records and we rerun to properly account for the probabilistic uncertainty of the inherent uncertainty of the ground motion, obviously that's not enough. And that's exactly, if you want my opinion, why the code in its current version is shifting from the mindset, let's try to predict how different the ground motions will be, and shift to what the impact is expected to be on the structure, no matter the scenario you're using for your ground motion. So I definitely agree with your question, but I think this is now bypassed by focusing on the structure rather than focusing on the response. A final comment is that, because your question applies to the case that somebody would do a proper, not simplified, spatial variability analysis, it's never a single run. You should account for ground motion record-to-record variability by running, as the code is providing, 7 pairs of ground motions or a larger number of ground motions properly matching the target spectrum.
Thank you very much. The next question from Paolo Michael. How would the spatial variability would affect the displacements on the two bridge ends, and if the boundary conditions change?
Okay, that's an interesting question. First of all, the code, its current version, its new version, is asking to follow these rules and these methods, and then calculate whatever the displacement should be, depending on the method you are using. Now, if I understand the question properly, in essence, spatial variability would probably increase the displacements at the abutments, if this is what I think you mean by bridge ends. And that's why it is increasing essentially the possibility of bounding in case of C-type abutments. Now, that's exactly the reason why this version of the code is providing methods to either calculate or increase all the displacements you're calculating, so that the gap you're designing for, maybe after this application of the methods, will be larger than the one you would calculate through the standard conventional uniform excitation.
Thank you. And regarding the gap size, it's a continuing question. How would this affect the size of optimum gaps when the concept of the dynamic intelligent bridge is implemented?
Now, perhaps you need to explain a little bit more exactly what you imply by dynamic intelligent bridge, but overall, yes, the size would change, because the size of the gap that you would calculate for a uniform excitation scenario would be smaller than the size of the gap you would calculate for the asynchronous excitation scenario, but obviously only in these cases that the code is expecting the problem to be significant, which means long bridge, long spans, different soils, 1D, 2D, 3D side effects, essentially.
Okay, and Mr. Michael asks again, my question is regarding the implementation. Can the spatial variability be implemented through the available commercial softwares?
All the simplified methods, effectively all, let me say what you could do. Uniform easily, like we do already. The static simplified method that we presented is just static analysis. In the previous version, in the current version, we can all do. Time history analysis, we can all do. The challenge in the previous code is that when this is needed, is to use a software to calculate these ground motions. If a design office is not able to deliver this, but this is required by the code, then there is the option to escape by applying the 20% increase. That's exactly the rationale behind leaving some space to the designers who are not able to apply the complex method. But in fairness, the complex method, it's like 5% of the cases. Because the bridge has to be very long, the span has to be quite long, the soils have to be quite different. These are special bridges, and for special bridges, most probably the design offices are able to deliver this.
Thank you very much. A very last question, a short one from Professor Butenweg. Could you give a short comment on the increasing factors of 20 and 30% for spatial variability? What is the background of that?
The background, Professor Butenweg, dear Christoph, is statistical. Because from 20 to 30 is essentially the transition from short length and short span to long length or long span. And statistically, this is how things increase, or the variability and the amplitudes of the engineering demand parameters increase when the span length or the total length increases or the variability of the soils increase. So it's based on the literature on statistical processing of hundreds, thousands of analyses during the last 20 years by a number of different groups, I would say.
Thank you very much, Professor Sextos, once again.
Pleasure.
I think now in our schedule, there is a short break